Hi, and welcome to B.1 Thermal Energy Transfers. It's quite a large topic, so I have split this tutorial up into two parts, just so you can break it down into more manageable chunks. So we'll start with learning objectives 1, 2 and 3, and basically we're going to look at the difference between solids, liquids and gases. We're going to define density and work out what the equation is, and finally we're going to look at the difference between Kelvin and the Celsius temperature scales and the all-important conversion factor between the two. On the left here we have a solid, and there are 5 things I'd like you to remember about a solid. They have a high density. You can see that these particles in a solid are very closely packed. They have a fixed and regular arrangement. You can see that there's a lovely pattern there. There are strong forces between those particles, and that's particular to a solid. They are not moving very much. They have low energy, and that's because they're not moving. It's a bit like me on a Sunday night. I have low energy, and I don't move very far from the sofa, if I'm honest. So I'm a solid on a Sunday night. Then we move to liquid, and a liquid has medium density. They're not as closely packed as the solid. There's an irregular arrangement, there's no pattern. The forces that bind them together are a bit weaker, and they have medium energy. There's random movements at low speed, and this is maybe like me on a Monday morning. I've got medium energy, and I move randomly, slowly, and that would be me as a liquid. And finally, our gases, they have a low density. They would be easy to compact and reduce the volume because there's such a low density in a gas. There's an irregular arrangement. There's no pattern whatsoever. There are no forces holding those particles together. They have high energy and they have free movement at high speeds. A bit like me playing TIG when I was 8. High energy and free movement at high speeds. You need to be able to draw those regular arrangements or irregular arrangements for solid, liquid and gas. Let's start with freezing and melting. This is our solid and this is our liquid, and we'll notice that the terms freezing and melting represent the changes between solids and liquids. Now this is a physical change. That means it can be reversed. So when you have a solid and you melt it into a liquid, you can reverse that change by freezing it back into a solid again. This is a physical change. Let's look at melting. When you heat a solid, it melts and becomes a liquid. The mass stays the same, but the particles gain energy. Now let's look at freezing. When you cool a liquid, it freezes and becomes a solid. The mass stays the same, but the particles lose energy. And that's what I'm talking about, this idea of a physical change. It can be reversed. We reverse what's happening. The particles gain energy and the particles lose energy. It's a physical change. Once we've got our object up to a liquid form, we can turn it into a gas, and it's a physical change, so we can reverse it back into a liquid again. And the two names we use to this, when we boil a liquid, it turns into a gas, that's boiling, and when a gas turns back to a liquid again, that's known as condensing. So for boiling, when you heat a liquid, it boils and becomes a gas. The mass stays the same and the particles gain energy. When we look at condensing, when you cool a gas, it condenses and becomes a liquid. The mass stays the same and the particles lose energy. Can you see some common themes coming through here? They're all physical changes, which means they can be reversed. They all have the mass stays the same. Okay, the mass doesn't change. But what does happen is when we're moving up a state, the particles gain energy, and when we're moving down a state, the particles lose energy. Let's have a look at two special examples. When we were looking at a liquid to a gas before, we were looking at the term boiling, which is where some really direct heat is placed upon the liquid. So it's in a kettle or it's in a Bunsen burner or something like that. But actually, if you were to just leave a bowl of water beside a radiator, some of that liquid, without being boiled or in a kettle, some of that liquid would turn into a gas. It would evaporate. And that happens just because the liquid slowly absorbs energy from the surrounding area. And then what that means is the particles gain enough energy to escape the liquid. So this change of state from a liquid to a gas is different from boiling because we're not applying direct heat. We're absorbing energy from the surrounding area. So when you're thinking about explaining evaporating, I'd like you to memorise these 2 points. Finally, something that not many people are that knowledgeable about is sublimation. And that's when we skip out liquids altogether and go straight from a solid to a gas. It doesn't happen very often, but something you might have seen it in is dry ice. If you've seen a demonstration of dry ice in class, you would see that solid carbon dioxide can turn almost instantaneously into dry ice, which is a gas. And that's known as sublimation. What we have here is, quite frankly, I was going to pretend that this was lots of particles, but actually I think it's just a big photo of ping pong balls floating about in the air. And what I want to suggest is that these ping pong balls floating about in the air represent particles in a gas. And the density of that gas is a measure of compactness, how close together those particles are. Put a gas out of your mind right now and let's consider the nucleus of an atom. The nucleus of an atom has some protons, colour them in blue, and it has some neutrons, and they would be, let's say, white. So let's make a few more. And what you'd notice inside a nucleus is that these particles, these protons and neutrons, are very closely packed. It has a very high density. And if you look at a gas, for example, what we've represented there with all our ping pong balls, or let's draw it again here. Let's draw these particles all spread out. With a gas, the particles are more spread out. They've got low density. And what becomes obvious to us is if we take that gas with low density, we can compress that gas together. 1, 2, 3, 4, 5, 6. 6 particles in that volume. 1, 2, 3, 4, 5, 6. We can compress a gas into a much smaller volume. That's because there's room between the particles to compress it down. We can't really compress a nucleus because they're already compact as much as they possibly are. So when we're considering the density of something, anything that has low density means that we can compress it together much easier. One key point about that is that the mass stays constant. There are 6 particles here and there's 6 particles there. The number of particles hasn't changed and the mass hasn't changed. All that's happened is the volume has decreased, which in turn has increased the density, and that's why it's so easy to compress a gas. Now, what is the definition of density? And this is unusual. The definition of density is the equation. So if you're asked to define density, you would write density equals mass over volume. Simple enough, okay? Density is given this symbol rho, R-H-O. It's a Greek letter, I think, and it's basically like a curly P. And it has units of kilograms per meter cubed. Or you can write it like this, like that. Or does it? Let's have a think. If your mass is in kilograms and your volume is in meters cubed, then yes, your density units is in kilograms per meters cubed. But imagine if your mass was in grams and your volume was in centimeters cubed. Then your density units wouldn't be kilograms per meter cubed. It would be grams per centimetre. Oh, I haven't written that very well. It would be grams per centimetre cubed. Imagine if your mass was in kilograms and your volume was in millimetres cubed. And guess what? Your units of density would be kilograms per millimetre cubed. So the units of density are basically determined by what the units of your mass and volume are. And the third learning objective we wanted to look at was the difference between the Celsius and the Kelvin scale. Both Celsius and Kelvin are two scales and they're used to measure temperature. In the UK, we're probably more familiar with Celsius. We would describe the weather as being, it's 25 degrees Celsius outside. I mean, don't get your hopes up. In Scotland, it's never 25 degrees Celsius. It's more like about 11 or 10. But still, we would use the Celsius scale. And in America, you would use the Fahrenheit scale. But scientists, we use the Kelvin scale. And the Kelvin scale starts at absolute zero with 0 Kelvin. And it goes all the way up linearly. And it goes up at the same intervals as the Celsius scale. So the reference point for the Kelvin scale is absolute zero, but the reference point for the Celsius scale is 0 degrees centigrade, which is the freezing point of water. For most calculations in IB physics, you're going to want to use temperature in Kelvin, which means you'll need a conversion factor. And the conversion factor is shown on the screen right now. To find the temperature in Kelvin, you simply add 273 degrees to the temperature in Celsius, which leads us on to the rookie mistake that most students make is not converting temperature into Kelvin in all calculations. Below the rookie mistake, there are some example past paper questions, and let me tell you, if you don't convert into Kelvin for these questions, you practically get 0 marks. So please remember that the Kelvin scale is very important in IB physics. Let's now head to your revision note template. The instructions on the screen will tell you exactly what to write and where, so I suggest you pause the video here, follow the instructions on the screen, and we'll get on to the next set of learning objectives. Let's go. Okay, learning objectives 1.4, 1.5 and 1.7 are all looking at the concept of internal energy, and we're going to deep dive into that right now. Candidates had difficulty with describing, in terms of energy changes, the molecular behaviour of water and steam during heating. I think we're all pretty comfortable with the idea of what the structure of atoms and molecules looks like within a solid, liquid and gas. But the difficulty arises when you try and explain the energy, the microscopic energy changes during that process of moving from a solid to a liquid to a gas and back again. So we're going to look at that in a lot of detail. And before we can really take that to the appropriate IB level, you need to understand what internal energy is. And folks, this definition is often asked in exams. So this is certainly one of the definitions that you should memorise before you approach your IB physics exam. The definition of internal energy is: the internal energy of a substance is the total potential energy and random kinetic energy of the molecules in the substance. So we're looking at potential energy and kinetic energy of the molecules. I'd like to have a look at this idea of random kinetic energy and total potential energy. I'd like to break them down a bit further so you understand exactly what we mean by those two terms, and then we'll talk about the phase changes and how they change. The kinetic energy, very briefly, can be described in 3 words as random, translational and rotational. Let me explain these terms in a little bit more detail. Random, I think we all have an idea of what that means. Translational is when an object is moving in a straight line. Translational, it has translational kinetic energy. So if we look at these molecules here inside this gas, they are all randomly moving in random directions in a straight line. So that straight line movement would result in translational kinetic energy. These molecules might also be spinning. So if they're spinning, they will have rotational kinetic energy. So the kinetic energy of molecules within a gas is made up of translational and rotational kinetic energy. The internal energy of a substance is also dependent on the potential energy between the molecules. And this potential energy is due to the fact that the molecules within the gas will have charges. They will have positive charges within the protons, they'll have electrons. The forces between these molecules will result in a form of electric potential energy. And I'll expand on that a little bit later on. Let's go back to kinetic energy just now. There's a really important relationship that we need to understand before we can go any further here. We know that molecules within a gas will have translational kinetic energy when they move in a straight line. We know that they also have rotational kinetic energy. Let's forget about rotational kinetic energy for a second and concentrate only on translational. You can imagine that each of these molecules will be, well, we've said it before, randomly moving about in different directions. Let me show you a picture actually, just to go back on this. Look at these molecules here. They are moving in different directions. They are going to collide off the side of the container. They are going to have different speeds. They're not all going to be travelling at the same speed. So it's impossible for us to say what the actual kinetic energy of those molecules are. But we can calculate what the mean kinetic energy is. So the mean, or the average kinetic energy of the atoms or the molecules, can be calculated. If we look at the mean translational kinetic energy of an atom or molecule of an ideal gas, what it turns out is that it is proportional to the temperature of the gas. And mathematically, we can show it through this relationship here. We've got a bar above the symbol for kinetic energy, so the average or the mean kinetic energy is directly proportional to temperature. Here we have some molecules bouncing around in a fixed body of gas. They have quite long vector arrows to show their velocity, so they're moving quite quickly. That means they have a higher temperature and a greater mean translational kinetic energy. So as they heat up, they move faster. We now have the same body of gas, the same molecules, but the temperature of the gas has been lowered, and that means that their translational kinetic energy, or the average translational kinetic energy, has decreased. You'll know that when you have two variables that are proportional to each other, there must be a constant of proportionality. And by finding out that constant of proportionality, you can form an equation that relates the two variables. Well, in this case, the constant of proportionality is 3 over 2 Kb, where Kb starts with the Boltzmann constant, and you can find that in your data booklet. So, if you wanted an equation to find out what the average kinetic energy of the molecules are within a gas, then you can use this Boltzmann equation here. I think it's really important to note that this equation will give you the average kinetic energy. But of course, the kinetic energy of the molecules in the gas have a range or a distribution of kinetic energies. And a typical range or distribution of kinetic energies of molecules is shown in this graph here. So when you calculate this average kinetic energy value, a key understanding that the examiners really demand of you is that not all molecules have that speed. Not all molecules have that kinetic energy. In fact, there's a range of kinetic energies which will affect other properties of the gas. Let's think about the potential energy of the substance now. Let's have a look at the solid state first of all. In a solid state, the electric potential energy between the atoms is large and negative. So it's a negative number. There's negative energy, electric potential energy, in a solid. As the substance is heated, the separation of the atoms increases slightly and the potential energy increases slightly. It's going from a large and negative number to a slightly smaller but negative number. Finally, when we get to a gas or an ideal gas, the molecules and the atoms are very far apart. And when they're completely separated, the potential energy is a maximum and has a value of 0. So the maximum potential energy we can have between the molecules is 0. And that means that there are no intermolecular forces between those molecules at all. With those two terms having been explained, and by the two terms I mean kinetic energy and potential energy of the molecules within a gas, let's now look at a fairly common graph you might have seen as water moves through phase changes from being a solid down here to a liquid up here to a gas up here. Anything underneath 0 means that water is in its solid form, it's ice. So between A and B, there's thermal energy being applied, it's getting heated up. And here's what's happening to the molecules within that block of ice. First of all, the molecules are gaining energy and vibrating more. You can imagine them within this very strict lattice, as we'd call it. And as it gets a little bit hotter, they vibrate around their equilibrium position in the lattice. As they vibrate more, their kinetic energy is increasing. But there's very little change in the mean separation between the molecules. They stay very close together. And for that reason, their potential energy stays much the same as well. So between A and B, what we see is the main change of the internal energy of the block of ice is that the kinetic energy is increasing. Now, of course, internal energy is equal to kinetic energy plus potential energy. So we can say that the internal energy is increasing, but mainly due to the kinetic energy increasing. We then get to section BC. Now, BC is where the bonds between the molecules are starting to break. And that takes a lot of energy. So as the substance is actually transferring from a solid to a liquid or from ice to water, a lot of the energy is taken up on breaking the bonds. That energy does not go into raising the temperature. The kinetic energy of the molecule stays the same because the temperature is not changing. And we learned earlier that the temperature of the molecules is directly related to the kinetic energy. So if the temperature is not changing, then the kinetic energy is not changing of the molecules at this stage. However, the molecules are getting slightly further apart, so their potential energy increases. At stage C, the block of ice is turned fully into water. Heat energy is still being applied, and we can see that the temperature of the water is increasing up to section D. Let's have a look at what happens to the molecules during that stage. During that stage, the molecules are moving increasingly rapidly. They're getting hotter. Their kinetic energy is increasing. But still, there's very little change in their mean separation. They're still roughly the same distance apart, which means there's very little change in their potential energy. As the temperature gets to 100 degrees Celsius, section D, there's quite a lot of work to be put in from the heat energy to break the bonds from a liquid into a gas. We're breaking them from being loosely attached here at D to being completely as far apart as possible at section E. There's quite a lot of heat energy required to do that. So here's what happens to the molecules at that stage. As before, the kinetic energy stays the same because the temperature is not increasing. But the potential energy increases by a much greater factor than it did before. And finally, we get to section E to F. This is in gas form, and the gas is increasing in temperature. And at this stage, we can see that it turns to gas. The molecules move even faster. Their kinetic energy is increasing, but the
the potential energy has reached its maximum of 0. That means that they are far enough apart that there is no potential energy or no intermolecular forces between the molecules. It's really important that you understand what is happening to the kinetic energy and the potential energy at each stage on this graph. This is where the examiners have highlighted the misunderstandings of students during this topic. And if we go back to our actual examiner feedback, you can see that candidates had difficulty with describing, in terms of energy changes, the molecular behaviour of water and steam during heating. So let's go back to that final graph. I'd like you to take a mental picture of this final graph, print it out, add it to your notes. This is what you need to be learning in terms of phase changes in thermal physics.
Wow, well, we covered quite a lot there, and now it's time to really summarise this in our revision note template. First of all, write down the definition for internal energy and make sure you commit that to memory. Write down the Boltzmann equation in your common formulae, and probably the most useful piece of information to put in your revision notes at this stage would be the graph we've just extensively talked through. The graph that looks at phase changes and what happens to kinetic energy and potential energy at each stage of melting, freezing and so on. So take some time to draw that graph in your notes and annotate it properly. Now's the time also to head to the knowledge questions for B1 and complete questions 1 to 5. Next up, we have specific heat capacity and latent heat. Let's go. So different materials. Let's suggest we have 1 kilogram of aluminium and 1 kilogram of water. And I'm kind of trying to emulate my flask of tea up here. If 50,000 joules of thermal energy is added to this aluminium and 50,000 joules of thermal energy is added to this water, they will increase in temperature by different amounts. The aluminium will actually get hotter than the water. I'm a poet, I don't know it. And this is due to a quantity called specific heat capacity, and it's got a small c. Specific heat capacity is defined as, and this is a definition you do need to memorise, the amount of thermal energy required to raise the temperature of 1 kilogram of a substance by 1 degree Celsius. So let's go back to our water here. If we had 1 kilogram of water, which I said we do, it would take 4,200 joules of thermal energy to raise that 1 kilogram of water by 1 degree Celsius. So if I want to raise water from 0 degrees Celsius up to 100 degrees Celsius, because I want to boil it for my tea, then I'm going to have to raise it by 4,200 joules times 100, that 1 kilogram of water, to bring it up to boil for me to put in my flask. So, specific heat capacity is the amount of thermal energy required to raise the temperature of 1 kilogram of a substance by 1 degree Celsius. Have you heard of Kelvin? Kelvin is another way of describing temperature increase. So in America they use Fahrenheit, in the UK we use degrees Celsius, and if you're a proper scientist you use something called Kelvin. And it's just a different scale on how we measure temperature. But if you increase your water by 2 degrees Celsius to 3 degrees Celsius, it's an increase or a change in temperature of 1 degree Celsius. It's the same as increasing the temperature in Kelvin from 200 degrees Kelvin to 201 degrees Kelvin. Changing the temperature by 1 degree Celsius is the same as changing it by 1 degree Kelvin. Now, the reason I'm waffling on about this is the units for specific heat capacity are joules per kilogram, and that makes sense because we're raising the amount of temperature of 1 kilogram of the substance per Kelvin. And you might have expected to have to per degree Celsius there. But if you're a proper scientist, we won't have degree Celsius, we'll have per Kelvin. So that's your units, and it's one that's worth memorising. And you don't really need to know too much about the Kelvin scale at the moment, just that that's where it appears in the units. When we add thermal energy to a substance, that will increase the temperature of the substance. If you take thermal energy away, it can decrease the temperature of a substance, as long as we're looking something in the same state. So if we're looking at liquid and we add thermal energy to it and it stays as a liquid, then it will increase that temperature. And the amount of energy that an object gains or loses depends on three things. It depends on the mass of the substance, it depends on the specific heat capacity, and the change in temperature. And your formula for thermal energy is, and this is the way we show thermal energy, it can also be shown as this, delta E, is M, which is mass, times specific heat capacity times the change in temperature. And sometimes you might see it as delta theta, and sometimes you might see it as delta T for temperature. It just depends. Please be aware of both of them. So you might see the equation as delta E equals mc delta T, or you might see it as we've got up here as well. Now we can use an equation triangle for this. You can pop your thermal energy up here, and it could be delta E up here as well. And then you can do mc delta T on the bottom, or delta theta on the bottom as shown. When you think about adding thermal energy to some water, let's say we've got some water here, and you add thermal energy, you put a flame underneath it. What happens is one of two things. The first thing that happens, it will increase in temperature. And the second thing that will happen, it will change state. And I'm interested in this idea of changing state. What happens to the energy when you change state, all right? And that's to do with something called specific latent heat. And when we're dealing with an increase in temperature, we're dealing with specific heat capacity. And when we're dealing with changing state, we're dealing with something called latent heat. Changing state. I have already told you that when we have a solid, liquid and gas, when we change between solids to liquids, we break some bonds. And what the specific latent heat of fusion, or the specific latent heat of vaporization does, is it breaks bonds. So let's look at this in more detail. Let's think about a solid to liquid change of state, and that's known as the fusion change of state. When latent heat is added, now latent is an interesting word, I'll go back to this in a sec, but latent means hidden, maybe in Latin. I don't really know things like that. I didn't learn Latin at school. Feel free to Google it and let me know. So when latent heat energy is added to, let's say, a solid, let's look at ice. When latent heat is added to ice, the bonds break in the ice and the solid becomes liquid, becomes water. When latent heat energy is removed from the water, the bonds reform and the liquid becomes a solid. It goes back to ice again. It's a physical change. But while that process is happening, while it's changing state, the temperature of that ice and that water does not change. So all the latent heat, all the energy that's going in to that system at that time, it's all going into breaking the bonds. It's not going into heating anything up. It's just changing the state. And it's the same when we think about this water and we turn it into steam. All the latent heat energy is added and the bonds break and the liquid becomes a gas. And when we reverse it, the latent heat is removed from the system, it's removed from the gas, the bonds reform, and the gas becomes a liquid. But during this time, again, I'll say it right, the temperature doesn't change. It stays at 100 degrees Celsius for water until all the bonds have either broken or reformed. There are two definitions that you need to know. One is the specific latent heat of fusion, and that's when we go between solids to liquids. And the definition is the energy needed to change the state of 1 kilogram of a substance from solid to liquid. So if we have a 1 kilogram of ice, it's going to need a certain amount of energy to turn all of that to water. And that amount of energy is known as the specific latent heat of fusion. During this time, the temperature is constant. The specific latent heat of vaporisation is when we go from 1 kilogram of water and we turn it into 1 kilogram of steam. Again, the temperature is constant at this time, and the specific latent heat of vaporisation is the energy needed to change the state of 1 kilogram of a substance from liquid to gas. It has units of joules per kilogram. Let's look at specific heat capacity. Specific heat capacity is the amount of thermal energy required to raise the temperature of 1 K of a substance by 1 degrees centigrade. What that means is when you add heat to the system, you're adding kinetic energy to the molecules, and the molecules speed up. And you'll notice a change in temperature, but not a change in state. When you look at specific latent heat, when you add that thermal energy, it doesn't increase the kinetic energy of the molecules, it increases the potential energy to the molecules, which means bonds are broken. And you'll notice a change. Oh, you won't notice a change in temperature. No. You will notice a change in state, but not a change in temperature. I did a deliberate mistake there to catch us out.
You know the drill by now. Head to your revision note template, follow the instructions on this slide, and we'll head on to the next learning objectives in just a moment. Next up, we're looking at how heat transfers from one body to another. And there are 3 mechanisms that heat can transfer to do that: conduction, convection, and radiation. It's important you understand how heat transfers using each of these vehicles. Let's go. Let's think about heat transfer to begin with. Heat or thermal energy can be transferred in 4 ways. 1, conduction. 2, convection. I'm going to go with 3 as radiation, and then 4 as evaporation. So if we wanted to transfer thermal energy, we could use either of those 4 ways to do that. But an interesting point to remember is thermal energy won't transfer from cold to hot. It will only ever go from a hot place to a cold place. That's the fundamental rule of thermal energy transfer. And it will only transfer if there's a temperature difference. If 2 bodies are both at 10 degrees Celsius, it's said to be in thermal equilibrium. And what that means is no energy will transfer between those 2 bodies. However, if one body is 20 degrees Celsius and the other body is in 10 degrees Celsius, then thermal energy will transfer from the hot object to the cold object until they both reach the same temperature. So this object will increase in temperature, this object will decrease in temperature until they meet thermal equilibrium. The first way to look at is conduction. Let's have a look specifically at metals because they're great conductors. Metals have atoms inside them and lots of free electrons. Can you see these little orange things? These are free electrons, and we looked at these free electrons when we studied electricity. And what those electrons can do is they move between the atoms and they vibrate. And they can actually collide with the atoms as well, causing the atoms to vibrate. Their role in transferring heat energy is that they pass the heat energy on by neighbouring particles vibrating along the metal. So what these little free electrons do is they hit the atoms vibrate, and by vibrating it increases their kinetic energy. And by increasing kinetic energy it means increases their temperature. So the way that heat energy is passed along a conductor is that the neighbouring particles vibrate and it passes that vibration across the metal. In non-metals, so something like glass or plastic, there are some free electrons but not enough.
So there's not enough free electrons for that passing of the vibration to happen. So that's why conduction happens best in metals. And you can see here we've got an iron. This bottom of the iron is a metal plate, and it relies on the conduction of thermal energy to heat up your toastie. Wait, what? We don't want to heat up a toastie with an iron? That looks delicious though. Is it only me that thinks a white bread, plastic cheese toastie is utterly delicious? Love it. Please don't use your iron to make toasties. On the subject of conduction, there is a new equation added to the specification that wasn't in any previous specifications, and it's to do with the rate of energy transfer. Basically, how quickly can a material conduct heat using conduction? And this equation here is one that you'll find in the data booklet, and it's one you have to be familiar with. There are no past paper questions to give an idea of how they will assess this equation yet, but it's a safe assumption that you'd be looking for the keywords, the rate of thermal energy transfer, or something like thermal energy is supplied at a rate of. And when you see those keywords, I'd be writing this equation down just to see if we can get the answer using that. Let's talk a little bit more about conduction, but you've got it already. Good conductors are metals because they have free electrons, because they contain free electrons which collide with the atoms and cause vibrations. Let's write that down. Cause vibrations. Good insulators, so things that don't conduct heat very well, are non-metals like plastic, glass. But funny you should say that. Liquids and gases are not good conductors either. They're actually quite good insulators in this case. So it would be very difficult for you to have conduction of thermal energy through liquids and gases. And the best insulator in terms of a conduction method of energy transfer is a vacuum, because there's no particles. So that's why I've shown this picture of space. What's in space? A vacuum. So you cannot transfer heat energy through via the method of conduction in space, because there's no particles to carry that thermal energy and to carry those vibrations. The next method of heat transfer is called convection. And I just want you to think about something just now. If you had a container, a closed container, and inside that closed container you had water, oil, and air, and you mixed it all up, what would eventually happen is you'd get some layers of things. And the layers would take a very specific order. And that order would be dependent on which one is most dense and which one is least dense. Basically, the least dense substance would go to the top and the most dense substance would go to the bottom. And I want us to bear that in mind when we're thinking about convection. In particular, let's look at this very cool lady sat beside a heater. What this heater does is it heats up the air around it. And by heating up the air around it, it makes the air less dense. So by heating up the air, it makes the air less dense. And something that's less dense will rise to the top. So that heater sends, that heater has the effect of sending hot air upwards. And guess what happens when it gets to the top here? Is it still close to the heater? No. So it gets more dense. So it cools down and it gets more dense. And what happens to more dense stuff? Well, it goes down again. So it goes down to the bottom here in a more dense fashion. Up here it's less dense, everything's a bit further apart. And then actually, as it gets closer to that heater again, what happens to it? Well, it gets hotter. So it goes back up again, and you can see there's a circular motion here. And that circular motion is known as a convection current. And we're going to look at them in a little bit more detail in a second. But let's have a think about particles that are stuck in a structure like solids. So a moment ago we were looking at metals. The particles that are stuck in the structure, they can't move in this convection current like particles that are not stuck in a structure can. So we're looking at, for convection, we're looking at liquids. They can do this because the particles can carry this idea of thermal transfer. And we're looking at gases. Whereas with conduction, we were looking at solids. So the main transfer of thermal energy in a solid is conduction. The main transfer of thermal energy in a liquid and gas is convection. I'd like to look at convection currents in a little bit more detail. The liquid and gas particles carry the heat energy, and the substance becomes less dense and rises, what we talked about earlier. During this process, the substance loses heat, so it loses heat up here, becomes more dense, and goes back down again. And then we find this idea of convection current. So if it gains heat from whatever the heat giver is. And let's look at this saucepan in more detail. So the water, let's start here. The water at this stage here transfers heat into the water particles, the H2O, if we're going to be sciencey. That means that they become less dense, so they rise to the top. At the top, it cools down and becomes more dense, so it falls down to the bottom, where it hits the heat again and then becomes hotter and less dense, and things start to flow round. It goes round and round and round in a circle. And that is how making your broccoli works, or making your pasta. Convection currents are set up inside the liquid that you're cooking your food in, and it's to do with the idea of density going more dense and less dense and forming this circle. It happens in saucepans. It happens in real life. So during the day, imagine you live by the sea. During the day, the sun beats down on us. Well, not very often in Scotland, but it does. And it heats up the land. It heats up the land more than it heats up the sea. That land causes the air around it to heat up. So the air around it becomes less dense and moves upwards. All sorts of things are formed, like clouds and so on. But as it goes upwards, it gets colder. So it falls back down again. And it falls back down again over the cool air water. So it goes along the cool air water to where it reaches the land again, and it heats up again, and a convection current's formed. And that's why it's windy at the seaside. Because a convection current is formed by the ground heating up the air around it, causing it to become less dense, moving upwards, and then a convection current is formed where the more dense air then comes back down over the sea. And at night it's completely the opposite, because at night what happens is the sea has been warmed up all day and it retains heat more than the air does. So actually at night time the sea is warmer than the air. At night time the sea is warmer than the land. So the convection current goes in the opposite direction. The convection current causes the air over the sea. The convection current causes the air over the sea to become less dense. So it rises, goes up into the sky, it then becomes colder and falls down again. By falling down, if it gets pushed towards the sea heats up and this convection current happens. So convection currents are the reason that we get wind. And finally, let's go back into our house. Let's hope none of you live in a house like this. Ugh, yuck. It looks very uninviting. And what's this drain for? What fluids are they hoping is going to go down that drain? But this is the only picture I could find that really showed two radiators. I don't think those radiators even work. So let's go to a diagram instead. We've seen this before, but what's going to happen to here is the air molecules around here are going to become less dense as they carry the heat. It goes upwards, less dense. It gets cold. So what happens is it gets cold and it becomes more dense. And it goes downwards and it starts all over again. The annoying thing about this is these are called radiators. And they shouldn't really be called radiators. They could, well, that's not true. Radiators is fine, but we could also call them convection heaters. And actually they do sell things called convection heaters. Well, I call them a fan heater. I don't know what you would call them. But have you seen these things that they've got? It's like a big hairdryer. You switch it on and it blows hot air out. They're called convection heaters because what they do exactly what they say. They send out a convection current of air. Whereas radiators cause a convection current, but they also give out heat via radiation. So this is our third method of energy transfer, and it gives out heat as infrared radiation, which is an electromagnetic wave. Do you remember the electromagnetic spectrum? There are radio waves, microwaves, infrared radiation, visible, ultraviolet, X-rays, and gamma rays. So infrared forms part of the electromagnetic spectrum, and they're basically lights that can travel through a vacuum, i.e. space. So when the sun gives out infrared radiation, that infrared radiation can travel through space and hit us here on Earth to make us feel warm, like this lovely lady is here. Look how happy she is. Happy. Because she's receiving some infrared radiation from the sun. Now, we wouldn't get heat transfer from the sun through convection or conduction because there's no particles in space. And conduction and convection rely on particles to travel. Radiation does not rely on particles, or a medium is the sort of term we use to transfer energy. We don't need a medium to transfer heat energy with radiation. Radiation, so these electromagnetic waves, these infrared radiation, travels at the speed of light. It can be reflected, but they can't travel through opaque materials. So if you've got black cloth, like on her legs here, they won't transmit through them. They'll just, the thermal radiation will be absorbed by this black cloth. So that means that her black trousers will feel a lot hotter than her red shirt because the black cloth will absorb the radiation, whereas, for example, this white bit of the cloth will reflect the radiation. Okay, let's condense all this information into our revision note template. Write down the equation for kinetic energy transfer for conduction in the common formulae section, and then I would go to the other notes section and note as much as you can about conduction, convection, and radiation. Let's extend on the concept of radiation and take it into something called black body radiation. I'm going to explain to you in a moment what that is. It's basically still looking at temperature and thermal energy transfer, but more specifically,
black body radiation and how we can use this radiation to determine the temperature of stars, and so on. It involves two very special laws that we'll discuss that will allow you to answer all the exam questions. And actually, I've decided to call this section Part 2 because it's quite a long tutorial and I felt it was better to split everything up into two parts. Let's go. Black body radiation. Let's talk through this. A perfect emitter of radiation would also be a perfect absorber of radiation and therefore would be perfectly black. Now, if you imagine an object and it absorbs radiation, it takes all that radiation and then quickly re-emits every single part of it, the object would appear black. And that is what we define a black body. A black body is something that absorbs 100% of radiation and re-emits 100% of the radiation. And the radiation that is absorbed and then re-emitted from that body is called black body radiation. So the radiation from a theoretically perfect emitter is called black body radiation. There are not that many perfect emitters in the world or in the universe. Stars are not, but it's quite good to approximate them into a black body perfect emitter. Probably the closest thing we have to a perfect black body emitter in the universe is the universe itself. If we look at the cosmic microwave background radiation, it emits as a perfect black body. Anyway, we approximate a lot of bodies into perfect emitters. I would like to look at black body radiation in a little bit more detail. And when you plot a graph of the amount of radiation emitted from an object, the intensity of the radiation, and the wavelength of the radiation emitted, you get quite a distinctive curve. Let me talk you through this curve at the moment. Let's have a look at this white star, which is about 5,000 Kelvin, which is not far off the temperature of our star. Our star emits visible light. It also emits some ultraviolet, because that's what gives us sunburn, we know that. And it emits some infrared radiation, because that keeps us warm. So the star emits a range of radiations over a range of wavelengths. But it emits some more than others. So our star would emit more visible light than it would ultraviolet or infrared. And the peak wavelength of that radiation, the wavelength that is most emitted by the star, can be found by looking at this curve. If we look at a hotter star, something that appears blue and is 7,000 Kelvin, the curve has the same distinctive shape. There is a peak radiation, and it does radiate over a range of wavelengths, but it emits more of everything, and the peak wavelength seems to be smaller. If we look at a colder star, the peak wavelength seems to be greater, and it emits radiation over a range of wavelengths, but less of every part of the wavelength. So what this graph shows is that hotter objects radiate peak electromagnetic radiation at smaller wavelengths. And that makes sense to us because if you look at the blue flame in a Bunsen burner, we know that it's blue, it's got a lower wavelength of light, but we also know that it's hotter. It's hotter than the orange flame. And that tells us a little bit about the astronomical objects. Blue stars are hotter than red stars. On a very basic level, that tells us which star is hotter just by looking at the colour of it. But there is a formula that we can use called Wien's law, and that allows us to find out more specific information. We can work out the wavelength for which the intensity of a star is highest using Wien's law. So we can say the peak wavelength of the star, and if we go back to the graph here, the peak wavelength for this blue star would be around about 450 nanometers. times its temperature in Kelvin is equal to 2.9 times 10 to the minus 3. It's a constant. And the units of the constant are mK. Please don't think that's millikelvin, that is meters Kelvin, because the unit of wavelength is meters and the unit of temperature is Kelvin. What that tells us is as the star gets hotter, the wavelength, the peak wavelength, gets smaller. A hot star or a hot black body will be radiating electromagnetic energy. And the amount that it radiates per second is known as the power, or its luminosity. We've seen from our mechanical studies that power is equal to energy over time, or a joule per second. And the same is for stars and astronomical bodies, or the Earth. Anything that's warm, it will radiate energy per second. And that power can be calculated for a perfect black body. And it's given by the Stefan-Boltzmann law. Once we know the temperature of the black body, or a star, or the Earth, we can use the Stefan-Boltzmann law to work out its total power radiated. So we can work out how much energy, electromagnetic energy, is being released per second using this formula. This is a constant. It's known as a Stefan-Boltzmann constant. It's in your data booklet. This is the surface area of the star, or the Earth, or anything that's radiating energy. And this is the temperature to the power 4. I'm going to highlight again, this formula here is for a perfect black body. So it's something that re-emits all the energy it absorbs. And it also assumes that the radiation from this star, or the Earth, or anything that's radiating the energy, obeys the inverse square law. That means that it radiates out energy in all directions equally, and it continues to infinity. And that's the end of topic B1. We have a few more things to do. Get your revision note template out and write down both the laws we've just discussed, write down the definitions of luminosity and apparent brightness, and complete part 2 of the B1 knowledge questions.